All right. Gallery view. Okay. And I think we're live. Our internet's a little slow today, so sorry we're delayed, everyone. Welcome back to Astro Chats. We're excited to have you with us for another exciting conversation. I'm your host and YouthAstroNet Community Coordinator, Erica Wright, and we'll get started in just a second. As a reminder for all of you out there, we hope you'll join in on the conversation either on Twitter or Facebook. You can use the hashtag Astro Chat. Post your questions. I'll be monitoring both throughout the conversation today. Again, that's the reminder. If I look away from the screen, I'm actually just looking for your questions to join in and ask any follow-ups or side chats. We want to know them all, and I'll ask them for us in today's conversation. So post those online. We really want you to be part of the conversation, although I always have plenty of questions too. So today we're going to be talking all about the sun and other spinning stars with our special guest, astronomer Dr. Stephanie Douglas. Thanks for being with us today, Stephanie.
Sure, thank you for having me.
We're excited to have you, and I'm excited to talk a little bit about the sun, something close to home. So I heard that you recently got a new position. So sadly, you'll be leaving us at the Center for Astrophysics, but that's very exciting for you. And I thought maybe because you're on to your next position, you could tell us a little bit about your pathway in astronomy and kind of what that's looked like.
Sure. So if you had asked me when I was, 10 years old, if this is where I would end up, I probably wouldn't have guessed that I would be an astronomy professor. I did always like astronomy. I was into it for as long as I could remember, but I was terrible at all of the observing parts of it. I could not make a telescope work to save my life. I could find almost no constellations, and living near Washington, D.C. may have contributed to that. But I never wanted to stay up late and watch meteor showers and stuff, but I love reading about astronomy. And so when I got to high school physics in 11th grade, I discovered that I really, really liked this way of thinking about the natural world and the universe, and found out that astronomy is just a subpart of physics. So I built on that and ended up going to college for astronomy, and then did my PhD. And now I've been a postdoc at the CFA here in Cambridge for 3 years now. And then hopefully in July, I'll be moving to Lafayette College back to Pennsylvania.
Wonderful, that's great. And we've talked a little bit with some of our past guests what a postdoc is, but maybe in case we have some new viewers today, you could tell them what that is.
Sure. Yeah, so a postdoc, it means a postdoctoral researcher. So sometimes your PhD is called a doctorate, and the postdoc is like an interim position. It's usually temporary, where you got your PhD, they're like, here you can be you can be a professional scientist without a PhD. They're like, here you got your doctorate now, here's your certification. And then you sort of go on to do some more research training for a while. So in my case, I have a fellowship. And so I mostly direct my own research, but other people say, they'll do their postdoc working for somebody else. So they'll be doing research in somebody else's group. But the goal is to continue becoming more independent on the way to becoming a faculty member.
Fantastic. That's a great perspective on what that is. So you're doing your own research, and I think you brought a little bit of that to share with us today. Is that correct?
Yep.
All right. So maybe you can share some of your slides and show us some exciting things that you're studying.
Yes. All right. So let's see if I can get this to work again. Okay. So that should be sharing a screen with a moon.
That's what we see.
All right. There we go. So yeah, so my hope is to talk to you today about the sun, which is our nearest star, and some other stars that also spin that are a little bit further away. And studying those other stars is mostly what my research focuses on. And if you're interested in following me, and I don't post a ton of astronomy stuff on my Twitter feed, but if you're interested in asking me questions or seeing what I post there, my Twitter handle is @StephTDouglas. So the question you may be asking is, why do I care about spinning stars? Why do I care about how fast a star rotates? And the answer is that we care because we want to know more about planets. So this is an artist's impression of a sun-like star, and in the foreground is what's supposed to be the edge of a planet. And everything we know about planets is sort of derived from what we know about the stars that they orbit. And this includes things like how old is that system? Earth, when it was very young, was not terribly habitable. So we want to know, are we looking at a young star or a young system or an older planet that might have had time to develop life? Unfortunately, the ways that astronomers usually use to figure out the ages of stars just don't work very well for a star like the sun or a lower mass star, a smaller star. And so one idea that people have been pursuing for a while now, and I'm one of them, is can we use stellar rotation, how fast a star spins, as a clock to figure out how old these stars are? So you're probably used to seeing the sun like this. On a nice bright day, there's this glowing thing up in the sky. And as I said before, the sun is our closest star to us. The Earth orbits the sun, and we get all of this light and energy from it. But if we zoom in and take a picture of the surface of the sun where we can see all the little features, we can see more detail. So this is, you can see that the sun still kind of looks like a white ball in this image, which is what you would see. Don't look at the sun, but what you would see if you could safely look at the sun. But you can also see there's these other little dots. And these little dots are called sunspots, these dark regions. And they're sort of the first evidence we had that the sun is actually a giant magnet. The sun is probably not what you're used to thinking about when you look at a magnet. You're probably used to thinking more about something like this, a bar magnet that you may have seen in like science class. So in this case, this is a bar of metal. It's got a north pole and a south pole, and north and south poles attract each other, north and north repel. And if you took a whole bunch of iron filings, so little pieces of metal that act like little compass needles, and what they'll do is if you put them in a space where there's what's called a magnetic field, a compass needle or a little bit of iron will align with those field lines. So you're used to using this to find north, but it can also point south, as we'll see. So this is what would happen if you surrounded this bar magnet with a bunch of iron filings. So you can see they collect around the north and south poles, and then they follow arcs from the north pole to the south pole. And this is what we call magnetic field lines, or they're tracing along the magnetic field. So this magnetic field it's called a dipolar field. So it loops from the North Pole around to the South Pole and goes back in again. And the sun has several components to its magnetic field, but a big component of the sun's field is actually a big dipolar field. It's like you stuck a bar magnet vertically inside the sun, and you get these big field lines that go from the North Pole to the South Pole. But what you may also, and that's what's represented by the red and blue lines here. But what you may also notice here is there's some smaller loops that you may be able to see poking off the surface of the sun. And those loops go through the surface in these things that we call starspots. So again, or sunspots. As you saw in the first image of the sun, there were these dark patches. And this is a zoomed in version of those. And these sunspots are the footprints of loops of magnetic field. So again, if we could follow those iron filings around a magnetic field here, you'd see that the loops go from one spot to another, or from one edge of the same spot to another. And so the reason that these are dark is that these little bits of magnetic field that are poking out through the surface, they make it harder for energy to get out of the sun. So the sun is very bright. It's like an incandescent light bulb. But if it's harder for energy to get out, patches of the sun look darker. And so that's why these look darker to our eyes. They're still really hot. It's just comparatively. And so what these tell us is that even though the sun has this big sort of bar magnet type magnetic field, it also has all these sort of little magnetic regions. And so that's what causes these star spots. This is just another way that we can look at this. So I've circled where the sunspots would be. This image is no longer in visible light, what we can see. This is an image in ultraviolet light. It's much bluer than the things that we can see. So it's showing much hotter, high energy things. And so the sunspots would be down in that orange circle. And then you can see the loops. Now, instead of iron filings, this is just really hot plasma. It's like even hotter than gas. And so it sort of arcs along these field lines and gets heated up. And that's how we can see where the magnetic field lines are on the sun.
Can I ask a question about this picture?
Yeah.
So one of the things we've been talking about is that some folks have been bringing photos and others have been bringing drawings, artist impressions, things like that. And we've been kind of talking a little bit about whether these are real images or kind of what we're looking at.
Yes. So this is actually a real image. This is from the Solar Dynamics Observatory or Orbiter. I can't actually remember. So yeah, this was an image. The Sunspot image from the previous page was an image. This one here, the central part is an image. It's another high energy image from one of the space observatories of the sun. But the lines, for example, are, we can't really see those. That's an artist's impression part.
Okay.
And this, for example, is another image of the sun, also by SDO. And in this case, this is actually a movie, so it's a series of images. So, oh yeah, what I was going to say before is I'm going to focus on the surface of the sun, but I know on Friday, Samaya Farid is going to come in and talk more about the really big loops of magnetic field that you get and the sun's outer atmosphere, which is also really neat. And so I hope you guys will also watch that as well.
Great. Yeah.
So yeah, back to the surface. So if we could sort of sit in the same place and take a picture of our view, the half of the sun that we can see repeatedly, we would see that these sunspots are not actually static. They're not fixed points on the surface. So this is a movie, again, from SDO. And if you look at one spot or set of spots, you can see that they're growing and changing. Some spots are disappearing, but also that sort of the same regions stay in the same place. And so you can track the sun's rotation just by watching these spots go around. And people have been doing this with the sun for hundreds of years. We know that the sun rotates about every 26 to 27 days. It's complicated because its surface doesn't rotate at the same speed at every latitude. So it's hard to measure the exact speed, but that's roughly what people have figured out. And the sun is nice because we can resolve its surface. Because it's so close to us, its light only takes 8 minutes to get to us. We can actually compare what's happening with the spots to what's happening to its total brightness. So this is going to be another movie. And so in the background is another video very similar to the one that we just watched. And in the foreground is a plot of something called the total solar irradiance, which is just a fancy way of saying the total brightness of the sun as a function of time. I forget what year this is, but it was happening in August into September. And what you're going to see is that there's going to be a spot that comes around, and the brightness of the sun is going to go down when that spot comes into view because it's darker. So there's the spot that came into view, and you can see, I'm pointing at the screen where this is happening. I'm sorry.
We can, if you use your mouse, we can see that on the screen.
Oh, good. It wasn't working when I did this. I did something similar on Monday. Yeah. So you can see as that spot comes around that you get this dip in brightness. It's not very big because the spots on the sun are very small relative to the surface. But we do get this little dip in brightness when you see a spot go around. And so this is the type of data that we have to look for. This front plot is what we have to look for from other stars. Because, for example, if we look at other stars, we aren't seeing their surfaces. They're all pinpoints of light. So in this case, this is an image of the Hyades Cluster and a whole bunch of background stars. You've probably seen the Hyades before. It's the closest star cluster, what's called an open star cluster, to our sun. And its 4 brightest stars, along with an unrelated giant, form the head of Taurus. And to give you a sense, because this cluster is so close to us, it's really big on the sky. Its stars are very spread out. So this is the moon for scale. And so even if we zoom in on this image, all we're really seeing are spots of light. And so we can zoom in even more. This is an image of it's a very low resolution image of just one sun-like star in the Hyades cluster. And when I should say low resolution in terms of astronomers means these pixels are really big, but we're still not resolving, even if we could differentiate, even if we wanted to differentiate between these pixels, they aren't going to show us the surface. This is just a really big image of all the brightness from the star at once. And this,
oh, sorry, I was just going to clarify for some of our young viewers, when we're talking about pixels here, I'm sure, right? Many of them have used cameras. Obviously, many of us have smartphones, and a pixel is just one little area of a detector, something that measures how much light fell on it, right?
Yeah.
And then we're displaying that back out on a screen.
Yeah, so the way that cameras work, whether they're in your phone or astronomical cameras, is you have a detector that's divided into a grid, and you're measuring you measure the brightness at each point in the grid. If you go back here, you can see when we talk about it being something being pixelated, this is also a very pixelated image, and it's a little hard to see, but you can sort of see I lost my pointer. You can sort of see that tiny pixels in this image. Whereas even though this is zoomed in, the pixels are much bigger. So it can be, if you have a really faint star, it can be hard. For stars like this, it's okay. And so this was taken with the Kepler spacecraft, which spent, I think its total mission was 7 or 8 years. So it spent a long time looking for planets in one particular part of the galaxy. And then it got a second mission pointing at a bunch of different locations, including part of the Hyades. And so this is just the image that it took around one star. And so what we actually analyzed is it took images every half hour for 70 days. And actually, a lot of what you can see in this image is actually instrumental noise. But effectively, the data that I was working with for this particular project on the Hyades was measuring this star's brightness in every single image, and then looking at it over time to try to reproduce that, something like the plot that I showed you earlier. And so what I'm assuming is happening here is that, like the sun, this star has spots, but that maybe its spots are really big or really concentrated into one big spot is usually what we assume about young stars. And so all we can see is that this spot or this group of spots come into view and out of view. Pardon me. And as the spot comes into view, just like with that solar example, the star gets fainter. As the star goes out of view, the spot goes out of view, it gets brighter. So the spot comes in and the spot comes out, and the spot comes in and the spot comes out. And we can see this with stars with other types of spots too. If they have a smaller spot, you're going to get less variability. And if the spots get even smaller, so this is kind of more like what the sun is, it's a lot harder to detect that variability. Luckily, at least, most of the Hyades stars show a lot of variability, so we think their spots are pretty big. And so this, for example, is the brightness over time, or what we call a light curve, for that same Hyades star that I showed you earlier. So we can see, oops. I keep losing my cursor, and then it reappears, and I don't know how that's happening. But anyway, so you can see that just like we expected from that cartoon on the previous page, the star is getting brighter and fainter over time. And the other thing that we look for is that pattern repeats. So sometimes stars might do weird things, like get really bright all of a sudden when they have something called a flare, or there's other types of variability. But what we really want to see is this, we know with rotation it should be periodic, because ideally the same spots should appear in the same places for a while. And so that's what we see here. You can see that up and down pattern is happening at about the same period as you go through.
Can I ask a question?
Yeah.
Typically, how long does a sunspot last on a star, or starspot, I should say?
So this is definitely an area of active study. So on the sun, actually, there we can measure it really well, and the spots actually don't last a full rotation. We often get them reforming in a similar spot, but the sunspots themselves don't tend to last a full, they last just a little bit less than a full period, which is what makes that determination of the solar rotation period more complicated is that you have to find the spot groups that stay even as the spots themselves are kind of going in and out. And what we think is happening on really fast rotators, so things with periods of less than a day or even a few hours, is that their spots seem to stay there for months, if not years at a time. They are very steady. So this is something in the middle, which I'll actually show on the next page. So here, this is just the same light curve that I showed before, but I've recolored it. So color just indicates time, it just indicates the time axis. So yellow was right when we started observing it, and purple was at the end. And what I'm going to do is I measured the period of the star to be 10.2 days. So I'm going to take the first 10.2 day chunk and plot it. And then I'm going to take the next 10.2 day chunk and overlay it on top. So the goal is to see, the period looks coherent by eye, but I want to see what's happening from rotation to rotation, from cycle to cycle. And so that's what's here. So this is called a phase folded plot. And you can see that in the background are the yellow and green points from the beginning of the observing period. And in the front are the purple and dark blue points. And what you might notice is that the amplitude of the purple points, so the variability amount from the lowest point to the highest point is a little bit less where in the purple parts than in the green parts. And what that suggests is that something's happening with the spots where we're not seeing as much contrast as they go around. So this could be because the spot is fading out, it's getting smaller, and so we see less variability when the spot is smaller because it just can't, the dark spot is not as big, so it just doesn't cause as much of a decrease when it comes into view. There's some other things that could be going on. So for example, it could actually be that there's another spot forming partway around the star, so your contrast gets less. So as it goes around, you're not seeing this bright side and this darker side. It evens things out a little bit. So there's a couple different things that could be happening here. And it changes from star to star. So this, we see this whole zoo of starspot properties just from looking at these light curves. And so, for example, the first panel here, you can see there's an overall up and down variability signature, but there's something else on top of it too. If it's a little bit hard to see, but basically there's some sort of like shorter period signal over, that's why the band is so thick, is because there's like a shorter period variability over top of the
so a smaller up and down. When you say shorter period variability, meaning like a smaller up and down.
It's a smaller up and down.
Okay.
What we think might be happening there is there's actually two stars. So they're both have spots and they're both spinning, but one is much faster than the other. And so they're together, they're blended together. And so we see the spots going around on both of them at the same time.
Wow. So sometimes when we look up at the night sky and it looks like there's one star, there might actually be two?
Yeah, it happens a lot actually. Sun-like stars in particular, almost half of them are in what's called a binary system. So there's two stars that are orbiting each other. And yeah, they're very common. So it's one of the challenges in a lot of things if you're looking for an Earth-like planet. The sun is actually technically atypical because it doesn't have another star in the system.
Wow, interesting.
Yeah. And so there's some other stuff that you can see. So in the top right panel, there's in the yellow and green cycles, there's a second peak. So there's a big peak where it gets brighter and then fainter, and then a little bit where it gets brighter and fainter again. So what we think is happening there is there's a big spot on one side of the star and a little spot on the other side of the star. So you see, and so when one goes into view, you get much fainter. And then when the other one comes into view, you only get a little bit fainter. And so, but that second spot seems to go away. If you look at in the upper right corner still, that peak to peak difference is smaller as you go forward and you lose that second spot. So we think we are still seeing the right period, but the second spot has gone away.
So the second spot is maybe lasting not as long as the bigger spot.
Yeah.
Okay.
Or yeah, there's other, I'm trying not to go into like all of the like weird things out there without having any cartoons to show you. But that is, and then in the bottom right plot, the original spot may have totally gone away. So you can see in the yellow and green that it had a really strong peak to peak variation initially, and then it just flatlines. So either the spot's totally gone now, or it's just the spots have spread themselves out so that even as it spins, you're seeing the same amount of brightness. It's not like you have a spotted region and a bright region where you see one and then the other. It's just all the spots are kind of equally spaced. And so you're not seeing a change.
Okay.
And these are from a different cluster that's the same age as the Hyades. But you can see that we just get this zoo of light curves. And what I use these for is really just as a way to check that the rotation periods that I'm measuring are basically accurate. But they're also just a really cool way to look at what the spots do on all these different types of young stars. I should have mentioned at the beginning, and I forgot, the Hyades is somewhere between 600 and 800 million years old. The sun is about 4.5 billion years old. So these are much, much younger stars. I think these stars are about as old as the sun was, I think a little bit after we got liquid water on Earth. Try not to quote me on that, but I think that's right.
Somewhere in that time.
Very early.
And so and I'm guessing because you're pointing out the age that you think things change over time in a star?
Yes. And the reason I should have said it is because I'm getting to my next slide here. So the takeaway point, basically, I take all those periods that I measured that I've been showing you all the pretty light curves for, and I turn them into just each star gets one number that's how fast does it spin. And what we find overall is that if you start from, say, 100 million years, you have stars that are spinning pretty fast with nice big spots. And as they get older, their spots get smaller and smaller, and the rotation period slows down and slows down until you get a star like the sun. So if you look at 100 million years, a star with the same mass of the sun, so this is probably what the sun was doing when it was that old, they rotate in about 6 days, 5 or 6 days. At 600 to 800 million years old, they're already to 10 days is how long they take to go around. And then when you get to the sun's age, again, you're at almost 30 days. So at least for stars like the sun, it seems like we may be able to use rotation as a clock, actually, because we can assume that a rapidly rotating star is probably young and a slowly rotating star is probably old. I'm skipping over a lot of the details that we haven't quite gotten that clock set up yet and calibrated. That's what I'm still working on. But roughly, this is the way that we're hoping to be able to figure out ages for planets sometime in the future.
I'm going to ask a little clarifying question there. You said for stars like the sun. Mm-hmm. So does that mean there are stars that aren't like the sun?
Yes. So we often talk about the sun. The sun, it turns out, is actually a quite average star, aside from the fact that it doesn't have a binary companion. But yeah, so sun-like stars are pretty common, but it turns out actually lower mass stars, so these are smaller, fainter, redder stars. They go to orange and then they go to red as they get cooler. They are actually much more abundant than the sun. They're actually easier to find planets around too. But their rotation may follow a slightly different track as they evolve. They live much longer than the sun as well. And so things seem to work neatly for a star like the sun, but there are a whole bunch of other types of stars. I care about the lower mass ones, which is why I'm talking about those. That's more complicated. And so that's something that needs a lot more time. There are also much hotter stars than the sun. So the types of stars that go supernova and that you hear about more frequently in that type of news when things go boom. those are more massive. So they're bigger and they're hotter and they live for much less time. I tend to ignore the vast majority of those because their internal structure is different. The lower mass stars have similar internal structure to the sun. The big ones are quite different. And so I only look at the ones that have sun-like internal structure, even if they're different masses.
Okay. So who knew there were so much variety in stars? And
it's a whole zoo out there.
Great.
So, but yeah, that was
okay.
As far as we were going.
Oh, so I ended on a great question then of moving on to kind of, so you were saying there's, obviously this is just a toe into the water of what you research because there's so much complication, right? There's so many different pieces that we would need to know to be able to understand all of your research, but this is a great kind of dip into that. One thing you mentioned a little bit, and I think maybe we have some time to talk about this a little bit more, was planets going around other stars, right? That this is maybe will help us understand the age of those. And I think maybe we could take a minute because we actually haven't had anybody to talk about exoplanets explicitly yet. And so talk about what that means and kind of just give us a little nugget of that.
Yeah, I'm gonna see. No, it didn't work out. Okay, I was gonna see if I had put in a bonus slide that would help with that, but it didn't. So yeah, so we're one of 8 planets that orbit our sun. We're the only one that we think has life right now, but people have been for at least 25 or 30 years now been looking for planets around other stars. So we think they should be there. And especially with the Kepler mission that I mentioned earlier, we've found thousands of them now. A lot of them aren't like Earth, unfortunately. So that's partly because of the methods we use to detect them. I'm going to turn off screen share. Well, there we go. Part of that's because of the methods we use to detect them. It's just easier to find planets around stars that are smaller, actually. And also that because the Earth takes a whole year to orbit around the sun, it's much harder. It's easier to find planets that are closer in. I feel like I'm losing track and just like talking about random planet facts. But yes, there seem to be planets around almost every sun-like star and stars that are smaller than the sun all seem to host some kind of planetary system. So a lot of the questions we have now really are these planets going to be habitable? And could they potentially have life? It's hard to detect whether they actually have life. So we're just trying to look for, things that could facilitate or help out life that as we know it, life like us.
Okay. And so part of your understanding these stars will help us to better understand the possibility of planets around them as part of.
Yeah. So one kind of funny thing that happened is that a lot of people for a long time thought these sort of low mass stars, they were like, well, they're everywhere, but they're kind of boring. So people like discovered them and learned some stuff about them. And then kind of were like, well, we're interested in the big ones, the ones that explode and live much faster. But since it turns out most planets are around these smaller stars, we need to learn as much as we can about these stars because otherwise, sometimes it's hard to tell whether a signal that you're detecting comes from the planet or just from the star. So I'm trying to think of a good example. So the basic one is in the way that we usually detect planets, you need to know something about the star. If you want to know how big the planet is, you need to know really well how big the star is. And just like I mentioned before, if you want to know whether the planet has been around long enough to have life, you got to know how old the star is because they're going to be basically the same age.
Probably. Okay. Yeah, and I'm going to point out for our audience, if you want to try your hand at detecting exoplanets, you can visit microobservatory.org and try out the DIY planet search portal. And you can actually create light curves based on a planet going in front of a star instead of the sunspot passing in front of a star for active data that you can collect tonight or tomorrow night at DIY planet search. Um, and so that's, I imagine another reason, right, is because for many exoplanets, when we discover them, we use transit methods. So a planet passing in front of the star. And it creates kind of a curve that looks a little bit like the sunspot curves that you were showing us.
Yeah, I actually, here, I'll show it. I left screen sharing before we could go to my bonus slide. So yeah, so here in the upper left is a screen cap from that video that I showed of the star spot going around. And then there's a schematic of what a planet transit looks like. And so they don't look, we can definitely tell the difference. So the star spot, even if it's just a single one, tends to look V-shaped, whereas a planet transit almost always has a flat bottom. And even then is usually shallower. The planet transits are usually shallower. But the other cool thing that I didn't even mention, so Kepler was a planet hunting mission. So it was staring at, thousands, tens of thousands of stars, trying to look for these little transit dips. What it meant is that it measured all this stellar data for free. All of us who are stellar astronomers basically just got all this bonus data that we could comb through to look for, to learn more about stellar physics. And then the people who were interested in the planets took the handful of stars that actually had planets and analyzed those light curves.
Great. So we've actually had a question come in online from Twitter. Sadie Coffin wants to know, why do star spots get smaller over the lifetime of a star?
So basically, remember how I said the sunspots they're like little, I don't want to call them imperfections, but they're little magnetic regions that are on top of that sort of big global field. And trying to figure out how not to get into the weeds of this. Basically, how fast the star spins determines how strong its magnetic field is. So when you send charged particles going around in a circle, you make a magnetic field. And the faster you send those charged particles around, the bigger the field is and the stronger it is. And so the young stars that spin super fast, they have really strong magnetic fields, which means they have really big spots because they have lots of these field lines around. And as they slow down, you're not making quite as strong of a magnetic field, which means you're not going to make quite as many spots and they won't be quite as big. And that just sort of continues with time. That as the star slows down, its magnetic field gets weaker, and so the spots get smaller.
Okay, so smaller, weaker magnetic field, smaller spots.
Yep.
All right, that makes perfect sense. Great question, Sadie.
That was a good one.
That's a great one. Yeah, I love seeing the questions online. I think of things that I don't even necessarily think to ask myself. So let's see. Maybe we'll take a brief minute to talk a little bit more about you as an astronomer. So you told us a little bit about your school and what you took and that kind of thing. But one of the things that I like to ask people just to give a sense of who you are as a person outside of an astronomer is maybe something about yourself that might surprise people, that doesn't maybe line up with the stereotypical, and I'll put that in air quotes, what people think an astronomer or a scientist might be like.
I feel like I fit a lot of the stereotypes, but
that's okay.
So I guess one thing that comes up a lot in stereotypes is this idea that scientists don't need to write and that they don't need to know a lot about the humanities. So one of the things that's been really important to me as an astronomer has been being able to write, being able to write well and being able to communicate my science to both other astronomers and to other folks out in the public in general. This came up, I remember hearing someone complain when I was in college. She was like, my son is going to be an engineer and he shouldn't have to write an essay to get into college because, he's just going to be doing math. Like, if you're not going to make the English majors take a math test, why should he have to write an essay? But it turns out that writing well is actually really important. And so I was not great at English and history in high school. It was really hard for me to learn to write essays, but putting that effort in actually was really valuable for me in the long run, because it meant that I'm pretty good at writing papers and proposals now and with sharing my work. And I really enjoyed the mostly literature and then like a smattering of other humanities classes that I took in college. I really like to read, even if I'm not great at the critical analysis side of things. Those were really fun classes to take. And I think sometimes a lot of scientists sort of don't they don't want to take the humanities classes. They see them as like, I just have to get these core requirements out of the way. But I think they're really valuable for sort of shaping who we are overall, and like giving your brain a chance to stretch in different directions. So I think I took one humanities class pretty much every semester that I was in college.
Yeah, I think that might be something people would find atypical. So that's great. And obviously you learned to enjoy them even if they weren't maybe your favorite thing in high school.
Yeah, I think even if they were challenging, they still were valuable in the end.
Great. So then I also like to ask one thing for our young audience who maybe is somewhere between middle school and high school, starting to think about careers. Maybe you're interested in science. What might be one piece of advice that you would have for them if they're thinking about science as a career?
So I think the thing that I just said about like being able to write well and speak well are actually quite valuable skills. And I think one thing that I hear from a lot of people is like, well, I want to do this, but like, I'm not really good at math. And it's true that math is quite involved in what we do. But I think the important thing is that, like writing, like things like foreign languages and sports, is that math is really a skill, and it's something that you can improve with practice. I had a pretty hard time with math in middle school, actually. And then for various reasons, kind of worked my way back up with it in high school. And I think the key there is to practice, like recognize that just like you wouldn't walk into a foreign language class and expect to be really good at it right from the start, it's something that can take practice. And so if you think you want to do something like this and you're like, well, I don't know that my math skills are good enough, it's perfectly fine to like have that be something that you're continuing to work on. Like, don't sell yourself short because you think you're missing some important skill that you can practice.
I think that's a really good point, is we often have a different set of standards for ourselves when it comes to math compared to learning, say, a foreign language or a sport, where we don't necessarily expect to be perfect at speaking Spanish if it's a second language for ourselves, or playing soccer if we're just picking it up. To start off, we know we have to work really hard and put a lot of time into doing that. But there is this stereotype in society that we should just be good at math, and if we don't start off at good, that just means we won't ever be good. Instead of, we just have to practice it just like we would any other skill. So I think that's a really great thing to point out. Thanks for that. Let's see, what other questions? Have we gotten any new ones online? Let's hope for the new ones online.
Yeah, people ask questions.
Oh, we've got another one from Sadie, and I think this is a great question, and I should be asking more of you this. What is the most rewarding part of your research process?
I have a lot of fun coming up with ideas, actually. I really like writing proposals and coming up with new questions and saying like, hey, I want to go get this data. And like that for me is really fun. Publishing papers is rewarding as well, but I really enjoy sort of coming up with new directions and new things to do. And gathering new data, going to the telescope is always fun. I don't get to do that as much as I used to anymore for various reasons, but I did a lot of observing in college. So heading off to a telescope, in that case down in Arizona, and just spending 4 to 7 nights there at a time. We were observing, basically indirectly observing the magnetic fields of some of these stars, very indirectly. And so that to me is also really fun. A lot of the beginnings of projects, I think, are my favorite part, which may or may not be good in the long run. But
you still have to see them through, but
yeah.
But then thankfully the paper is also a rewarding part for you, so that gives you incentive.
Yes.
So speaking of kind of coming up with these questions, this is one thing I've been trying to ask some of our visitors is, I think often we see these questions that scientists ask and we go, how did you even think to ask that question? So maybe you could share with us a little bit about your process for kind of narrowing down a question that maybe is a tangible thing to start answering.
Yeah. And so I think actually this is also something that's a skill, and that I would not say I've mastered at all. But I think one thing that's really valuable is like, if you're watching a talk like this, or if you're like reading an article about something scientific, any questions that you have, like that's not a sign, not necessarily a sign that you didn't understand something. It could be one of two things. It could be there was something in the article that it wasn't clear, or it was aimed at something that was a little bit higher level and they assumed you had some background knowledge that maybe you don't. And so it's worth writing down your questions or asking them to the person giving the talk, like in this case, so that you can go and research them later and get the background knowledge. But it's also worth writing down your questions because maybe they're a question that no one's seen before. And especially like as I've gone on and I've read more and more sort of scientific papers, writing down those questions, sometimes they get answered. Like I write this question down and then I read another paper a month later where they've answered it. And that can be kind of sad because it means I don't get to pursue that question. But it also is a really good sign. It means that I read that paper and I said, hey, this is the next step. And somebody else who is more senior to me had also said, hey, this is the next step. And so that was kind of a good sign that I was asking the right questions. And that also meant that when it came time to sort of move out on my own, start asking more of my own questions instead of purely working with the questions that my advisor and I came up together, I had kind of this backlog where I could go through and be like, hey, I never found a paper that answered this question. Maybe that's one that I can pursue now. And I still do work with mentors on figuring out what exactly is the right question to ask. So it's definitely a long process, but it's definitely something of just encourage that question asking side of yourself, even if all it is that you write it down and go try and Google it later. It's really good practice for seeing the unknowns in what you're looking at.
I think that's a great suggestion, just writing down our questions. So much of science is being curious and asking questions, right? Like you're not going to get an answer unless you first ask the question. There's a lot that has to go into it afterwards, of course, and you've shown us a lot of that hard work that has to go into it. But if you don't start asking the questions, you're never going to get the answers. So I think that's a great tip, just to keep a notebook with you when you listen to talks, go to talks, read something and write those questions down. I think that's a really great piece of advice, because even if you out there don't have the background knowledge that somebody like Stephanie might have, your questions are going to build over time as you build that background knowledge. And like you said, it's a skill that needs practice. So thanks for that piece of advice.
Yeah.
Let's see. Checking in. So we are starting to close in on the hour. Let's see if maybe we'll ask one more question. Or I also like to give an opportunity if there's anything else you'd like to share with our audience, whether it's science or something that you just think might be valuable for them to know.
I do always like sharing pictures of the telescope I used to go to, so I can take a couple minutes and do that. But if there are other questions, we can check those first.
Not yet, so let's see your pictures.
Cool. Again. Yeah, so like I said, when I was a graduate student, pardon me, when I was a graduate student, I spent a lot of time at an observatory in Arizona. It's called MDM Observatory, which used to stand for a couple of university names, but doesn't anymore. And so it was these two telescopes here. So the big one on the left, it's a 2.4 meter telescope. So I'm going to mess that up. It's like 7.5 feet across the mirror. And then on the right is a smaller telescope. I didn't use that. I just watched a lot of sunsets over it. So inside the leftmost dome here, you can see a little bit of the telescope structure. And this is the telescope that's inside that dome. So the mirror is in, okay, I get it back? Nope. So the mirror is in the bottom round white part there, is the main mirror. There's a secondary mirror in that silver circle at the top. So the light comes in, hits the first big mirror, bounces up to the smaller one, and then down into all the instruments that are hanging off the back of the telescope. And so I would fly down there for the longest run I did was 10 days, which was a little ridiculous. These pictures were all taken on a run in January of 2018, where I was there alone. So this is what the control room of this telescope looks like. And I'm using every single one of these monitors, including doing multiple things on some of the monitors. So it takes a lot to run these telescopes, and bigger telescopes, you have like one person whose job it is just to drive, and they've got like 12 screens with all the like information about the telescope coming in so they can watch for problems. But this is something that I really have fun with, is going out to the telescope, trying to think. You can see, I wish I had my pointer was working. So on the rightmost screen, you can see sort of a sky map. So that's what we're using to make sure the telescope's pointed in the right place. The screen up on the wall is a lot of weather data, because we have to make sure it doesn't like rain on the telescope, or that it's not too windy and it might like blow things around in the dome. There's the second monitor on the desk. Those two little stars on there are what we're using to keep the telescope pointed in the right place. So it'll always make sure it can see those stars in the right place. And then the next few are all gathering data. So it's all the controlling the imager itself that we were using to take pictures. And yeah, like I said, we watched a lot of really pretty sunsets. Of course, the pretty sunsets mean we couldn't observe, because as you can see, there's a ton of clouds overhead. But this was sort of the gift that we got given for the nights that we got weathered out, was really pretty sunsets. So this is another part of astronomy that's really rewarding, is getting to go to telescopes.
Fantastic. All right, so we're almost at the hour, but we've just had a comment, and I think I would love for you to respond to this.
Yeah.
First, they said thank you. Which, yes, thank you, and I'll thank you again in a minute. They've really enjoyed your talk. This particular person says they've experienced astronomy and science kind of feeling inaccessible and unapproachable. So what do you think are some of the best ways to make astronomy more welcoming and to combat imposter syndrome? And for those of you out there that don't know what imposter syndrome is, it's this idea that, you know, we get into science and we feel like we don't belong here. Like maybe they've made a mistake and we're not as good as everybody else when we get into science. And of course, those are feelings that they're real feelings, but they're not true. We're just as valuable. All of us belong here. We've put in the same amount of work. So maybe you could address that for us for a second.
Yeah, imposter syndrome is definitely a challenge. And I should say that I've been lucky in that I've not been in too many situations where like I've directly been challenged, like by other people telling me specifically that I didn't belong. So one thing that's important to me for belonging is making it clear that like, this is not, none of us are like really geniuses. Like this is a thing where we're all doing hard work. It's unfortunate that we can't say this as easily, but like this takes work from all of us. And it takes a lot of emotional effort, and it takes a community. So I think one thing that really helps is finding mentors and finding examples, but especially mentors and people who can sort of help reassure you and talk to you about the things that you're good at. So my PhD advisor was pretty good at that, where we would do periodic reviews where I would be like, well, I'm doing this all right, but I'm like not doing this as well. And he'd be like, you are fine. Like you're doing all right. And I have a lot of mentors that do that, which is really helpful. I think one thing that I'm trying to get better at as well is to look at ways that we can change the way we think about class problems, and the way that our classes are run, and the ways that we structure research projects and things, so that it's not, that it doesn't assume that everybody is, as I admittedly was, so that we don't assume that everybody is really good at like sitting in a lecture and learning a bunch of math off the blackboard and then like being able to convert that into problem solving later. Like that's something that I care a lot about, is changing the way that our classes is structured. I know that's not super helpful. But yeah, I think the other thing to do is try to look at yourself and what you're good at and recognize that whether or not that's visible, there's space for a whole wide range of skills to be successful in astronomy. There are people who are really successful with like really good math and computer science skills. There are people who are really successful because they're really good at teaching. Some people are really good at like writing and sharing things with others. And there's a whole boatload of ways to be successful. And so look at what you're good at and see what projects and things about astronomy you can find that are related to that, rather than saying, oh, here's what I call the average way of doing, like the typical way of doing things, and try to fit yourself into that. There's a space for, you know, a whole wide range of skills, including yours.
Fantastic. I think that's a great piece of advice. And I think one other thing I want to point out to you is that, as you've noted, as our audience has hopefully you've seen, we've had some really fantastic visitors in these Astro Chats that all want to hear your questions. Like, that's why they're joining us to be part of these Astro Chats. And they all want to support young people like you going into the field. So don't be afraid of that. Many have shared their contact point, because they're open to questions, and maybe can help you find somebody nearby that could be a mentor. Oftentimes, if you email your local university, somebody would be open to talking to you about the field of science. So don't be afraid to do that. And even if they don't personally have the time right now, they might be able to point you to somebody else that can, because we all have ups and downs and how busy we are. But thank you for that question, Sadie. I think that's a really good point. I think science can feel intimidating. The field has, you know, as we look at it historically, been certain types of people, and we see them as, you know, Einstein, right? And we're like, oh, everybody has to be Einstein to be part of the scientific field. And that's just not true. There's lots of hardworking people just like you and me that are in science. And so I think that was a great way to put that. And I really appreciate that, Stephanie. So thank you for the questions out there. I really enjoyed hearing them. Hopefully you did too, Stephanie.
Yes, those are all great questions.
And thank you so much for being here to answer all our science questions and our questions about being part of the scientific community. I really appreciate you being open to answering those, and for being here with me and our audience.
Yeah, thank you for having me, and thank you everybody who tuned in. Feel free to follow me, find me on Twitter, or ask, I guess you can ask more in the Astro Chat, and I can try and answer questions there as well.
Yeah, absolutely. Use the hashtag Astro Chat. Even outside of these live sessions, we're answering them. We'll find our I'll find our colleagues like Stephanie to answer them. So continue asking those questions. Join us again tomorrow. We have Juhan Wu at 10 a.m. who is going to be helping us take a glimpse into the web-like structure of the universe. So we're going to be going a little farther out into the universe, and hopefully you'll join us at 10 a.m. Eastern time, so bright and early for those of you on the West Coast. And we'll look forward to seeing you then. Thank you again for joining us, Stephanie.
Yeah, thank you for having me.
Have a great night, everyone.
Good night.